everybody. So last time we talked about how we can use orbital diagrams to figure out where our electrons are living, and we can use that periodic table of elements. If you remember, we have the S block here on the left. We have our P block, which is right here. You have the D block, which is right in between the two. And of course, the F block is the funny area down here that is always at the bottom. That's your F block. And we can use that periodic table to figure out most likely where our electrons are living. Now, most of you might say that seems a little inconvenient. Well, thankfully, there is a nice shorthand method for showing the electron configuration of an atom. It's called electron configurations. So all they are doing is finding the number of electrons occupying each sublevel and using a superscript. So now instead of writing lots of up arrows and lots of down arrows, we are going to use superscripts. So if you remember our first sublevel that we get to, here's our S block. If you start here at the top, that is our 1s. And if we were to do hydrogen, for example, our hydrogen has one electron. And that one electron, if you look back at that periodic table, is the first one we run into. So that is going to be in the 1s sublevel. So if we were writing our electron orbital or our orbital diagram for hydrogen, we would get to the 1s and we would have one upspinning electron. Now instead of having to write it up arrows and down arrows, our electron configuration, instead of writing up arrows and down arrows, we're going to use a superscript. So we're still going to write 1s, but now instead of writing these up and down arrows, we're just going to tell how many are there. So this would be our 1s1. Here's our big difference. Now let's try another one. So if we were to do oxygen, for example, let's first write the orbital diagram like we did the last time. So taking a look at our periodic table, let's get rid of this back here. Here's our oxygen. So first we start at the top. Here is our 1 area, and this is our 1s. We completely fill it all the way to our helium. So that means we have definitely filled that 1s block. So let's go ahead and write that down. So 1s is full, so that would be 1 up arrow and 1 down arrow. Now let's continue going. We got to go down to our second row here. So we are now in the 2s orbital area. So let's go ahead and see, do we fill this first area here? Yep, we haven't made it to our oxygen. So let's go ahead and write that down. So we've made it to our 2s location, and it has both an up spinning electron and our down spinning electron. All right, let's see if we can finally get to oxygen. All right, we're now all the way straight over into our first level of our P block. So this section here is our 2p area. And remember, we have our X, our Y, and our Z plane. So there are 3 different sublevels in this orbital. Okay, so let's count how many times over we go into to get to our oxygen. So we're going to have 1, 2, 3, 4 electrons divided up into our 3 sublevels. So let's try and write that out in our orbital diagram. So once again, we are in the 2p area, but you have 1, 2, 3 suborbitals, and we have 4 electrons. So first they will fill by themselves, just like how a school bus will fill their seats before you start to double up with one another. And then we have 1 extra one that's going to do the opposite spin and pair up randomly with that with an electron. Okay, so that was a whole lot of work. But if we do the electron configuration for oxygen, we're going to do the same exact thing. We're still going to have our 1s, our 2s, and our 2p. that we can take from the idea of the periodic table. But we got to figure out how many electrons we're going to have in each subsection. So because of our orbital diagram, we don't even need to look back. So we have 2 electrons here in our 1s, so we're going to use that in the superscript position. We also have 2 electrons here in our second s level. So again, we're going to use that as a superscript. And now we're going to get into our final 2p area where we have 1, 2, 3, 4 electrons living. So we're just going to put that as a superscript of 4. So if you ever are in doubt that you don't have enough electrons, you can always add your superscripts. So your superscripts, if you were to add them for oxygen, we have 2, 4, 8 total in our superscripts here. Looking back at our periodic table of elements, we have 8 protons, meaning we have 8 electrons. Looks like we have done this one correctly. All right, let's take a look at this electron configuration for oxygen. Now, in this question, it is asking you why the correct electron configuration is the one here on the left, and instead it doesn't spread out our electrons. So take a second to think about it. Back to the rules that we talked about last time, how we have the Aufbau principle. Goodness, I can't write tonight. Aufbau principle. We also have the Pauli exclusion principle and the Hund's rule. So whenever we're thinking about the Aufbau principle, we're going to go into our lowest energy first. And the fact that we have an electron choosing to go into a higher energy state, denoted by this 3, says that can't be right. It's going in the wrong direction. We always want to be at our lowest energy level. Think of how you're most comfortable. If you're most comfortable, you're probably laying down. That's because that's your lowest energy state. So automatically that should show some bells and whistles going off in your head saying, hey, this can't be right because we did not completely fill that p orbital. So there's that full explanation for you if you'd want to write it down. So let's try to write the electron configuration for a phosphorus atom. So first of all, you're going to want to locate your phosphorus on your chart, and here it is. So let's try and start from the top and work our way all the way down to get to P. So we're going to start in our 1s orbital, and it looks like we are able to completely fill it. So we're going to write down our first set of electron configuration orbitals. So you have the 1s, it is completely full, so you have 2 full electrons in there. Going back to our periodic table of elements, we're now going to go down 1 row. We're now in the 2s block. So do we completely fill this block? You better believe it, we haven't made it to our phosphorus yet. So we're going to add 2 more, and it is in our s block, so that must be 2s2. All right, now we're going to go straight across to our first P block, and remember this is our 2P block, and we still have not made it to our phosphorus yet, so we're going to have our 2P with 1, 2, 3, 4, 5, 6 electrons. So let's go ahead and write that one down. So we have 2p6. Whoops. All right, now going back down to our next row, we're going to go into the next S block, which is 3s. We still have not yet made it to our wonderful phosphorus over there, so we're going to check these 2 off, saying that our 3s orbital is full, and we would write that as the energy level of 3, S because that's the shape, and again, it is full of 2 electrons. Once again, we're going to go straight over because we like to go in straight lines here in chemistry. And we're finally going to hit our phosphorus. We're going to go over 1, 2, 3 times. So that means our final thing that we need to add to our electron configuration is the 3p, and our superscript will have the number of electrons here, which is 3. 3p3. Now let's double check and make sure that we have all of our electrons accounted for. So we're going to add our superscripts. All right, let's check. We have 2 plus 2 is 4, plus 6 is 10, plus another 2 is 12, and finally plus 3, that's a total of 15, and that is exactly how many electrons phosphorus has. So we must have done it right. If you want even more of an explanation, we can also go through the PowerPoint here, showing you even the orbital diagram. So something that is missing from our electron configuration is showing how our electrons in phosphorus are not all paired up. And if you want to look back at your rules, that is because of the Hund's rule, where they are going to go into separate orbitals before they start to pair up. So once again, if you need to, you can always start by making the orbital diagram here and then translating it like we did before. Or if you like the shortcut, you can also write it as shown the first time in our 1s2, 2s2 idea. So it is up to you. Whichever method is foolproof for you, I want you to do that one. Alrighty. Now with all that being said and done, there are a few exceptions, and that's when you get down to your transition metals. So for those of you who need a refresher, the transition metals are going to all be in this D block. So that's all of these ones shaded in here that are like a reddy purple color. So those are all of your transition metals. That's when we start to have some differences. So for example, if you were to do the electron configuration for, say, chromium or copper, they would look something like this. It's a little longer. That's okay. The rules still apply the exact same way. However, there is something different. See how this 3D and the 3D for both of these are not completely full, and yet we have something in higher energy levels. That is something that we haven't run into before. So that automatically should be screaming at you, hey, there might be something wrong. So the actual correct electron configuration is to have your 3D either half full or completely full. And what they'll do is they will borrow from the slightly higher energy level in order to make this occur. It does not happen very often. Let me repeat that one more time. It does not happen very often. So if you do have a question like this on a test, I will tell you. I will tell you when there is an exception, so that you can be looking out to make sure you know exactly when to do this type of borrowing from different sublevels. So do not freak out. I have complete faith in you because, again, I'm going to tell you when there is that exception. So let's try one last example and then we are all done for the night. So we're looking for the correct electron configuration for sulfur. This is not an exception, so use your regular rules. So again, we can just check right away. We have our 1s2 completely full, so all of those look great. Our 2s2s are all completely full, so those look great. 2p6, here's our first signal that something's off. So A is automatically eliminated. So now we're down to 3 options here. We have all of these 3 saying that our 2p6 is completely full. Check. Our 2s, whoa, we can never have that many electrons in our S sublevel, so that one's gone. And finally, we can count to figure out that the B does not have enough electrons.